Hello friends, सबको नमस्ते. Today in this video we will make a chest X-ray classification model which tell us that particular chest X-ray is suffering from pneumonia or it's a normal chest X-ray. Okay. According to that we have a data set. This is a data set containing two folders, test and train. In test we have two folders, normal and pneumonia, and same for the train. Okay. So let me open my let me show you how the images look like. This is a pneumonia images and this is a normal chest X-ray images. Okay. So this is a Jupyter file and a weight file. I will tell you how you can train your model and how you can download a weight file. Okay. So let me open this Jupyter file in my Google Colab. Okay. This is a Jupyter file. Let me start. So before that, let me tell you how you can connect your dataset which is present in your Google Drive to your Jupyter file. Okay, so go to your Google Drive. This is your let assume this is your dataset. Go to your share. Anyone with the link, copy link. After copy, paste it here, and from here till here you have to copy this ID. You can see you can say that this is a unique ID for your dataset. Okay, after that you have to paste this unique ID here in place of this. Okay, this way you will connect your dataset which is present in your Google Drive to your Jupyter file. Let me run this. This is a, you can say this is a package or library. This way it will download the zip file from your Google Drive. See, it's downloading. See, it's representing the dataset zip file. After that, unzip the file. It's done. See, test and train, two folder, and each folder contains two folder, normal and pneumonia. Okay, so let me close this, and now these are the libraries which we use for our creating the model and for the pre-processing of the images. This is our OS for directories, Torch. Here the framework which we are using here is a PyTorch. Here Torch for the libraries, random for random choice, Torch for and for layers, plotation, transformation of data, transform for data augmentation, and dataset, optimizer, data size for creating a data loader, app for ReLU, image operation means pre-processing. Here data loaders. Okay, dataset to load a dataset from the directory. Let me run it. See here, torch.device means we have to specify that which device we are using. We are using either CPU or a GPU. Okay, for that, if torch.CUDA is available, if it is true means GPU is available, means CUDA is available, it will send device value will be CUDA, otherwise device value will be CPU. Okay, now it's saying we have a CUDA, it means we are using GPU. Now we have to plot the graph. This plotting is give us the detail that how many images is present in a train directory of particular class, whether it is a particular class like pneumonia or a normal chest X-ray. So train directory, here image directory folder, you can save two folder name, normal and a pneumonia. Number of images classes means each, you can say it it will make a list of the I can say the length of the number of images of in each folder, normal and pneumonia. Okay, now we have to iterate over the image directory folder. After that, it will give me the list of all the images, name of all the images present in that particular folder. After that, we have to append the number of images present in that particular folder. This way we will know how many number of images present of particular classes. Okay, see now, see it giving me two list, in which one list it representing me the number of images of particular class, second it representing the class names. Okay, now here plot per bar graph will plot the images. Image directory folder give me the labels. A number of images means can say the values, and colors is light, with which color I want light blue. X labels, Y labels, values. This way it show me how many number of images of particular class. Normal we have around 15 around. Okay, 1500 or less than 1500, and for around pneumonia number of images we have a 1600. Okay, now we will plot the images from the train directory. Here we will first go to the directory, then the folder, then figure. Basically here figure representing the entire plot, and X here is for the iteration of a iteration towards the subplot, but here it is in a 2D dimension. After using ax.rebel, it convert into from 2D to quantity dimension for ease of iteration towards the subplots. Okay, now plot the subplots. Here 4 into 4 means 4 rows, 4 column, and each figure size of subplot will be 20 by 16. Okay, now we have to iterate over it. Now here we random select the folder, whether it is normal or pneumonia. Okay, randomly select the folder name. After that we will list all the images present in that particular folder, and then how we will generate the image path. See, image directory images means the image direct images, basically this image directory, basically this one. Oh, let me separate it so that you will does not get confused. See, here first is image directory, means train directory. Inside of train directory, which folder is selected randomly, we have to give that folder name, and after that we have to select randomly which randomly select the images from the normal folder name, or either from the pneumonia folder name which is selected randomly. Okay, this way we fetch the image path. After fetching the image path, we have to open that image, and class name will be itself with the image folder name. Okay, you know that pneumonia is a class name, and normal is a class name, and it's also a folder. So the class name is the image folder, and we have to represent them in a grayscale. Okay, the default IMSO CPAP value will be Viridius, but we don't want that color format. We want gray color format. Okay, this way we are representing the images. Let me run it. See, it's a normal chest X-ray. This is also normal. This is also normal. See, in most of the pneumonia, see, you will see that white spot above the in the chest X-ray is more than in a normal. See here, more white spot, more white spot. Normal, you can say in normal chest X-ray, you will does not see more intensity of white spot will be less in normal chest X-ray as compared to the pneumonia. Okay. Now let me make a data augmentation and transformation. And why? First thing, data augmentation is used here because we have a number of images is around 1500 1600, and this is the quantity is less on number of images. So to avoid the overfitting, we use data augmentation. Data augmentation basically increase the variety of the images and make the model more robustness so that it increase the accuracy. Okay, that's why we apply data augmentation, because it provides a variety of the number of images and also avoid the overfitting. Now first we will change the, you can say, RGB image into a grayscale image. Why we are converting the images into grayscale images? First, increase the computation speed. Second, you can see the chest X-ray is does not represent any RGB color, red, green, or blue, or a different color. It's just representing the images in a white and black. Okay, so it doesn't require any RGB images. We just use a grayscale images. It is enough for the model to learn a complex pattern from the grayscale image. Okay, now these are the pattern: random crop, flip with 50%, rotate with plus or minus 15 degree, and small shift for sharing, add slide for robustness, and convert to 10. Now this two thing is important. Convert the image into the tensor, and this normalizing the pixel value. Or normalizing the pixel value is just say that we can represent, we can say values in a feature map, or we can say values of the images will be on a certain scale. Every value will come to a certain scale. So when all the values come to a certain scale, you can say that no one feature will get dominated to another feature. Every feature will act as a balance. Okay, so there will this way we apply transformation, and this thing from here till here, this thing does not require to be performed, or you can say perform after training on a testing time. On testing time, only these two things and converting the image into a grayscale is just enough. This thing is just required to add a variety of the images on a images during training time, so that our model get robustness. So it doesn't require it after training. Let me run this cell. Now we have to create the data loaders which we use for training. Okay. So here dataset image folder, we just have to give the image folder train and transform and apply transformation to it. Train, or this means here dataset will automatically fetch the class name folders and the images in it. Okay, we does not have to manually assign it. Since we are not manually deciding it at which index value is representing which class name, we have to know that this function, how it define the image index value to which class. So for that we use this dataset.class2index. It gives us that which index value is representing which class name. Now since we do not have a validation dataset, okay, so to get the validation dataset from the trained dataset only, we are doing this. Train size should be 80%, so 0.8 into length of data will be give me the train size will be 80%, and validation size will be length of train data minus train size. Okay, means 20%. After that we will create the random split will be used, so that it split the this dataset into two part: train dataset, validation dataset, according to the size. Yes, we have to give the size. Train size will be 80%, validation size will be 20%. Okay, now this way we will create the train data loader. In data loader, just we have to give the train data set, batch size will be 32, shuffle will be there, number of worker will be 2. Okay, validation data set, train batch size, shuffle will be false, and number of workers will be 2. Now we have to print length of train data set, validation data set, and class index. Let me run it. See, length of train data set is train sample will be 2451. Train data set means 2451 will be the images for train dataset, and validation dataset we have 613 images for the validation dataset. Now length of the here train dataset length will be 2451, and not here, will just not become here, has to come val data. Okay, let me run it again. See, means val data contain 20 batches, and each batch contain may 32 images, and train data contains 77 batches, and each batch contain 32 images. Okay, now let me show you one thing. Let me show you. Now train dataset contain 2451 images, and divided by 32, it give me 76 batch will be there to contain 32 to contain the images. Let me show you. If int value will be there, 76 into 32. Okay, 2432 images is used in a 76 batches, minus how many numbers of images we have? 2451. Means 19 images is present in the last batch. Okay, in 77th wedge, 19 images is present, not 32 images. Okay, this way it's work. Now, I already told you that it automatically assign the index value to the class name. So to know that, we have to print it. See, it's assigning 0 for the normal and 1 for the pneumonia. Now we have to plot the images here. Sample.lib, we have to iterate over the trained data like this. Iterate first, it create the iterator here. Next will show give me the result. Here sample basically the images, and labels is just is representing the labels here. Sample. Okay. Let me show you one more thing. Let me in set title. Let me print it. Okay. Now one more thing I want to print. New line, and what is that thing? It is labels I, so that I will show you how the labels look like, so that you get a more clear picture about that. Okay, let me first run it, then I will explain you. See, now you get a more clear picture that 0 is how it's defining the index values. So this normal 0 and 1 for this. Let me first explain it so that I will show you this. I have explained this to line above in the code. Okay, this is the class names according to this. See, 0 for the normal, so I have assigned 0 key for the normal and 1 key for the pneumonia. Now we iterate over the images samples. Okay, samples basically contain the number 32 images, and labels contain 32 labels of 32 images. Now here, why see, in transformation we already convert the images to grayscale. To represent the grayscale images in a IAM, we have to CMap grep, because the CMap default value is Viridius, and you will get confused. Now why we have used permute here 1 to 0? Why? Because when we use transformations and to tensor, when we convert it to tensor, it basically convert the image dimension from HWC to CHW. Now for the plotting, the dimension should be HWC. So to convert that dimension, we have to use permute 1 to 0. Okay. Now here we are setting title, class name, labels.item. Basically give me the labels. Okay, a label value, and after label value we can use class name as a key to get the class name, and label side I will printing it just for the explanation. So this way it's used. Okay. And one more thing, that data augmentation apply, or I can say activated only when we iterate over that. Okay, before that it will not get activated. See how variety of the images produced. Okay, now it's this is the model which we use. Let me explain you one by one. Okay, here NN module, you can say this is a base class for our CNN class, and here we are initializing it. Okay, why we are using NN module as a base class? Because NN module contain most of the functions for which we have to use during training, that like a forward function, backward functions, and some other, and also manage the images. This all the functionality is available in NN module base class. So that's why we have to initialize it. Okay, to you can say to use the functionalities like this. And here we are initializing it. Here we are giving them. Here we are initializing it. Now this is our first convolutional layer. Okay. in channel basically is the, you can say, number of channel is which we are using. Number of channel we are using here 1, because we are using grayscale image. If we use RGB images, the input channel will be 3 here. Output channel basically gave us the, you can say, number of filters which we are using. Okay, now we are using 16 filter for the first layer, and kernel size is the, you can say, the window size which slide over the image will be 3 by 3. Now wedge normalization is number of features is 16. And what is use of wedge normalization? Basically, one thing, it's avoid the overfitting. Second thing, it normalize the feature map values, which basically ultimately increase the computation speed. And second thing, you can say that all the features, you can say no one feature will get dominated to in other features. Okay, this way it's helped me. Now and max pull 2D dimension is kernel size will be 2D and stride will be 2D. Stride, what is the use of stride? And kernel size, you can say the window size which slide over the feature map. Basically the feature max use of feature max pulling will be decrease the dimension of the feature map. Let me show you what is the stride meaning. So stride, stride, CNN. Okay. See, if stride will be 1, see, if stride is 1, it will slide to one row one row at a time, and slide from above it slide one sorry, when it slide towards the right side, it will skip one row, one column at a time, not one row, one column at a time. If slide from above, if this green window, it slide from the above, it skip one row at a time. Okay, this way stride 1 x. Now if stride will be 2, see here, you can say here red is the first step, first computation, here green is the second computation, and here blue is the third computation, you can say. In after completing the first computation, when it has to perform the second computation, it has to skip this 2 column, because stride value is 2. It skip 2 column and it's perform here computation. Here max pooling basically gives us the maximum value present in it. Okay, after completing this computation, when it comes to the third computation, it has to skip 2 rows from the above. Why skipping 2 rows? Because stride value is 2. This way it's work. Okay. See one more thing. You can see that after using stride 2 and stride 2, the feature map values. This whole thing is a feature map. Feature map value get decreases. Okay. Not values. The dimension decreases. See here now second thing, for the second layer, input channel will act as the we can say the depth of the output of the first convolution layer. In first convolution layer, number of filter which we are using is act as the depth of the output of the feature map of the first layer. Okay, so input channel will be 16, and output channel number of filters we are using 32, kernel size 3, number of features 32, batch kernel stride and 2. Okay, this way we'll make second layer, same for the third layer, fourth layer and fifth layer. After fifth layer, we flatten the layer. Means let me show you this thing also. See, this is a simple example. Let's assume this is a feature map. After using a flatten function, it converts like this. Okay, same way we are doing here. So after converting the number of neurons, what is the dimensions? Dimension will be 5 into 5 into 500, 512. Okay, because the output channel is 512, output filters is 512, that's why. So we are converting them into a number of neurons according to it, flatten it, and after flattenation we are using three fully connected layer, or you can say a dense layer. In fully connected layer you can say a number of neurons is there. Okay, we do not say there is a feature map, we say number of neurons, and number of neurons uh, in as an input is calculated after the flatten only. So here number of input neurons is 5.5 into 5 into 512, and output number of neurons is 1024, means each neuron of is connected to after layer. Okay, let me show you this thing also. Okay, best. See, this image is perfect. See, after flatten, this you can say this is a flatten. You can say this is on neurons, and after neurons, this neurons, how this output of the first you can say after the first fully connected layer, you can say this is a number of neurons. So each neuron is connected to the previous neurons values. It see, it's one neuron connected to this also, this also, this also, this also, this also, and same way for the second neuron, this also, this also, this also. This way the connection acts after flatten and the fully connected layers. And now output number of neurons is 1024. Here also we use Gaussian normalization because neurons also have a values, we have to normalize them also. Here for the second neurons, input feature will be 1024 because previous fully connected layer have a number of, how many number of neurons? 1024. Same way for the third and last layer. In last layer we have input feature is 128 because output number of neurons is 128 for the third layer. But here for the fourth layer, output number of neurons should be 3. Okay. So the output feature for the last fully connected layer should not be 2, should not be 3, it should be 2 because we have a 2 number of classes, normal and a pneumonia. After that we have connected to that, after that last fully connected layer is connected to a softmax layer. Why we are using a softmax layer? Because the neurons values not act as a probabilities values. So to convert that values into probability values, or we can say that the probability, after converting them into probabilities values, we can use that probability values as a score. So that's why we have to use a softmax layer. Okay. See here in this init constructor, we are not connecting the, you can say, connecting them the layers. We are just describing that how many numbers of layers we are using, how number of neurons is there, how many number of filters is there. These things we are defining here. We are not connecting them. Now henceforward the function we are connecting them. You can say that's x dot convolution layer, first convolution layer, then batch normalization, now f dot relu. See, using of the activation function in any CNN model is just to add the non-linearity in a CNN model. Non-linearity means if suppose there is no we do not use any activation function, the model will not learn complex pattern. It acts as a linear model, but we do not want that. We want that model should learn complex pattern also. So to add a non-linearity, we use activation function. And f.relu means relu activation function is one of the activation function. The how it's work, let me explain you. Suppose if the values is less than 0 or a negative value, the value will replace from negative value to 0, and if the value is greater than 0, the value will remain the same. This way the relu activation function work. Now relu, after relu, pole. Same way for the convolution layer, second convolution layer, third, fourth, and here x is acting as a image. Now flatten, now fully connected layer. Same way, the way we describe here, we have to connect them same way. Now you have to see that I am defining them line by line or layer by layer, but there is another way that I can do that, because I can convert this 4 lines into one line also. Okay, But just to easy to explain to you that you can easily able to understand each line one by one easily, I am using this. I am connecting them one by one. Okay. First convolution layer, then batch normalization, then ReLU, then pull. Same way for the convolution layer second. Same way for the fully connected layer, fully connected layer, then batch normalization, then ReLU activation function for that. Now last layer, fully connected layer, we do not have to batch normalization and ReLU. Just connect them to softmax because this is the last layer which give us the output. Now these are the summary. Okay. See here, last convolution layer output will be 5 into 5 into 512. Okay. These are the number of parameters. Here we are using cross entropy loss because we have more than one classes. We are using Adam optimizer here. Here model parameter is just you can say weights values which has to be trained during training. Learning rate is 0.1. I tried different learning rate, but 0.01 is best for my model. Okay, and epochs I am here using 30, and this is training, which is I already run this cell because I want to complete this. I want to show you. Okay. Okay. Now these are the libraries. Not library. Sorry. These are the list: training loss and validation loss and training accuracy and validation accuracy, which store the values at each epoch. See here. Initially, I set best validation loss to infinity. Because we are using model checkpoint, one of the facilities which we will use to save the best model among the epochs. We are using learning rate scheduler because we want to change the learning rate value according to the durations which we decide. Okay. Now here we are using learning coastline area optimizer. We have to pass on optimizer because optimizer only updates the weights according to the learning rate. Here Tmax values is epochs value is 30. Now see, now we have to use the for loop epoch model. Now mode of the training is here, model is train here correct basically you can say store the value how many prediction made by the model on an image is correct. Basically store the value how many predictions is correctly predicted by the model. Train learning loss basically store the loss value at each batch. Okay, now we are iterating over the trained data. Just to know that the model and label should be on the same device, we have to use this data.to device and label.to device. Now optimizer.0 grade is to set the gradient value to 0. Why we are defining the gradient value should be 0 at each batch, not epoch, at each batch we are defining. Why? Because it's suppose the during current batch iteration, previous gradient value will get accumulated if we do not use this function. If the previous gradient value get accumulated, weight value will get updated, but its updation will not be you can say correct updation will be there. Okay, so to correctly update the weights according to the training, we have to set gradient value should be 0 at each batch. Now pass some images, loss, it first calculate the loss. Here loss dot backward, basically calculate the weights value according to the loss. Here here updation of the weights does not take place. Here computation take place. Okay, optimizer dot step basically updates the weights. Now see here train running loss. Loss dot item basically give me the loss of the model or of each batch. Okay, and here we are saving the train running loss of each batch in a train running loss batch. We are not saving, we are adding that from the previous last value. Now here this prediction basically like this. Here prediction will be 1 for one image, 0 for the second image, 1 for the third image, and same way it's going on till 32 images. Okay, Torch or mesh give me two things: output. Output, we have to pass the output value. Two things means the index value and the prediction. But we want predictions, and according to the prediction, we compare based with the labels. And here some basically give me the till here till this thing for one batch. This thing give me that how many predictions are correctly predicted by the model. How many prediction the value will give me. Okay, and we have to uh, save it in a correct variable. Okay, now see why we are dividing in the trained data and why we have to divide in a trained data set. Because see, train running loss basically you can say storing the values for batch, not for the not for the number of images images present in a batch. Okay, it's just keeping the loss value for the entire batch. But here it's giving the values for num of you can say for the entire images present in a batch. So that's why for when we print the length of the trained data, it give me the number of batch present. Okay, now when we print the length of the trained data set, it give me how many number of images is there. So this whole thing give me prediction number, correct predictions made by the model, and this thing give me you can say loss for loss of the model. Okay, now we are appending them in a train loss and a train accuracy, and now we have to print the masses. Now this thing, this during validation only, from here till here, whole things is same with the training time, but these two lines are different. These have a great meaning. Bit torch with no dot no grade basically mean that there is no operation, there is no gradient, no, there is no operation take place. Now mode of the model is an evaluation model. We now means we are now evaluating the model, that how much our model is performing on an unseen data set. Okay, this thing is different, but entire thing is same for the same as a training. Okay, now here we are saving the model, or we can say we are using model checkpoint functionalities here. Okay, see epoch dot loss validity best model best validation loss. Initial best validation loss value will be infinite. Okay, but after see that epoch validation loss is less than the best validation loss, we have to update the validation loss value. Now we have to make the checkpoint point path, means we have to save the model. Now we are saving the model. Okay, torch dot save model dot state dot date checkpoint path. Okay, now this is you can say with validation law we are displaying the masses. Now scheduler dot step should be in a epoch for loop, not in a validation for loop, and training for loop, because if training, you can say scheduler dot step learning rate will change after each epoch only, so that's why it should be in a epoch for loop. I already run this cell, so till the best model is saved in a 21 epoch with 95 accuracy, and validation loss will be 0.35. Okay, let me explain you this thing. See here, training loss and validation loss is a list which we have defined, and epoch log give me values that 0, 1, 2, 3 for this values how many epochs we have used. Now r dash means straight line, r dash means a dash line, label with train loss and validation loss, and we have also want to define the legends. Okay, this way the legends is present, dash line, train, validation loss, and same for the accuracy. Here r is a red line. Okay, so see, now this is our current graph means after training how see how it's showing me loss, accuracy. Okay, let me run this cell. It's showing the error. Why? Election order directed object has no attribute to. Okay. One more thing. Model equals to CNN. Okay. So this way we load the model. We have to first define the object, then we have to load the static load.torch from where the model is saved, and we have to define the device, because model and this thing has to be in a same device. And now we have same thing during validation we have to evaluate. We are evaluating the model. Now during testing also we have to we are evaluating the model. So the state of the model will be evaluation. Okay, now see. Uh, One more thing I want to tell you, that what all the pre-processing we have done on our image has to be performed during testing also. Okay, so first we have to give me the test directory, then the folders will be saved here, a normal and a pneumonia, and this is the process of the you can say this thing is not used. So this thing is a pre-processing which we have performed on our image. So here it transformation where you can say where variable which we have described above. See, let me show you. Where it's gone. See this thing, this transformation variable. Okay, and this is a pre-processing. And see, unsqueeze basically you can say expanded dimension of the image. See, during training we are passing the batches. In batches you can say the dimension is like this, 32 images of size 1 channel 224 into 224. This is the size of the batch, or one batch you can say. Now same way we have to define the image batch, image dimension. So to convert the image dimension from CHW after transformation, the image dimension has converted to CHW. From this, to get this VCHW, we have to unsqueeze the dimension, unsqueeze the image, so that it converted to 1360, not 60, 224 and 224. This thing has to be performed. Okay, now this two line I already explained you. These are the class names. Now we have iterating over the range. 16 image has to be able to plot. Random is like the folder name, pneumonia or a normal. And here it first describe all the images present in that number of name of the images present at folder. Now here it getting the image path. First trace directory, then image folder, which is already you can say class name, normal pneumonia, and randomly choose the image from that folder. Now first open that folder. We have to convert that image in a grayscale. Then preprocessing function, which I have already defining here. And after that we have to give two devices, because image should be on the same device where the model is. Now we have to pass the model image to the model, and argument must give me the prediction of that image dot item. Now class label, according to that prediction we can define that which class a particular image belong to. And here we are plotting the image. CMap should be gray, because I already told you the default value is radius. And see, we are printing prediction label, prediction will be label, and actual will be image folder name, because image folder is act as a class name. That's why we have to print it. Now let me print it. Let me plot the images. Stern, see, normal, pneumonia, normal, pneumonia, normal. See, normal pneumonia. One mistake is there. Normal, pneumonia, normal. From 16 images, see, one thing also, pneumonia, but actually it's normal. Okay, pneumonia, 3 wrong. Means from 16 images, 3 predictions are wrong. It's a nice, you can say nice accuracy. So our model is ready. Now you can download this weights value from here. Okay. After downloading this weights value, you can create your own Streamlit web app, and you can deploy that model. Okay, you can do anything from this model. This thing you can get your best model with 95 accuracy. You can see that the last model which is saved last model which is saved on 21 with value accuracy is 95. Now you can use this. So friends, video is over. I explained you each and everything with a good explanation. Please subscribe my channel, comment and like my video so that I can get motivated to do more work for you, to give you the more knowledgeable work, more knowledgeable video. Okay, thanks to you, thanks to all.